Hi everyone, I'm Isha Paliwal, a master's in computer science student. I'm excited to share with you a fascinating project I've been working on at the George Washington University, focusing on the prediction of mood swings using machine learning techniques and a rich data set from Kaggle. This is a vital discussion on one of the most challenging aspects of mental health management, mood swings. In the realm of mental health, mood swings are not just everyday ups and downs, they're intense, often unpredictable changes in emotion that can severely impact daily living and overall quality of life. For individuals suffering from conditions like bipolar disorder, borderline personality disorder, and major depressive disorder, these mood fluctuations are a harsh reality that can disrupt personal relationships, professional commitments, and self care practices. Traditionally, the diagnosis and management of mood swings have relied heavily on subjective assessments, self reported symptoms, and clinical observations, which, while valuable, are fraught with limitations. These methods can vary in accuracy and often miss the nuanced patterns of mood changes over time. This is where my project comes in. Using advanced machine learning techniques, I aim to predict mood swings by analyzing a comprehensive data set of mental health indicators. My goal is to create a tool that can provide objective, data driven insights into an individual's mental state, significantly improving the accuracy and timeliness of interventions. This project is not just about technological innovation, it's about changing the landscape of mental health care, offering hope and improved support to those who navigate these challenges daily. Join me as we delve into the intricacies of this project and explore how data science can make a real difference in the mental health field. So, for this, we our approach is basically to collect the data, and the key objectives is develop and evaluate a machine learning model capable of predicting mood swings by analyzing a comprehensive mental health data set, bridging the gap between traditional subjective assessment methods and objective data driven approaches. So, this model structure and model selection we will discuss in more detail in the next slides. My objective is to develop a robust model that enhances mood swings prediction by leveraging my multi-output classification techniques. The proposed approach over here is first we will collect the data and then clean and standardize the mental health data set for analysis. We will perform EDA or exploratory data analysis to identify patterns and potential indicators in the data that correlate with mood swings. Then we will create the models by applying machine learning to predict treatment outcomes based on multi-feature profiles. Then we will validate our model by testing the accuracy and testing the accuracy with unseen data sets. Finally, the future aspect of this project is to do some clinical integration by by and then by translating the model predictions into actionable treatment recommendations. This step is a future step, and I have not yet worked on it. First, the data collection. The data was collected from Kaggle, was hosting a variety of mental health studies, and the one which I used focuses on various indicators relevant to mental health conditions like timestamp, gender, country, occupation, self-employed, family history, treatment, days indoors, growing stress, changes habits, mental health history, mood swings, coping struggles, work interests, social weakness, mental health interview, and care options. Here, the target column is the mood swings column. For data cleaning and pre-processing, we have used we have handled the missing values. So for that, handle the missing values. So you can see we have loaded the data, and over here The self-employed had the highest number of missing values, that is 5,193 missing values. So we have imputed it with the mode values of the column. We have dropped the timestamp a column as it does not provide any relevant information for the analysis of mood swings. And then we have removed the data, the duplicate columns. Next, we have worked on EDA, the performed EDA. So uh, these are the results of the performing the EDA. So as it was categorical data, we did not do the normal descriptive analysis of the by which we do with numerical columns, or created histograms and those other to analyze the data. We have we have rather analyzed the data and checked for the unique values count of each categorical columns, which you can see over here. We have created the columns distribution of all the uh, column distribution in graphical method for all the columns. And this is the target column mood swings, which has three kinds of data: high mood swings, low mood swings, and medium mood swings. You can see that they are all this is very uniformly distributed, and we can analyze them for our model development. We have also calculated the proportions of all the unique values of categorical columns. Then for the next step, we have, this is the same, the performance of EDA. Then for the next step, we have done encoding of the data. For that, we have done it's done in three ways. Label encoding, which transforms categorical variables into unique integers. So we have used the columns like gender, self-employed, family history, treatment, coping struggles for the same. Then we have for all the other columns other than country, we have applied one hot encoding, which which is an approach to create a binary column for each category, uh, and give it true and false value based on the data set. For country column, we have done we have used leave one out encoder, which is uh, which is good for to manage high cardinality and with minimal data leakage. This technique replaces each categorical value with the mean target value of all other samples where the category appears. Now, for the model development, we have used multi-output classification, which is useful to predict multiple target columns simultaneously, addressing the problem of correlated outputs in the dataset. For base classifiers, we have used linear SVC, logistic regression, naive-based, random forest, and XGBoost to determine which yielded the best performance in the multi-output scenario. Finally, to compare and evaluate the model performance, we have calculated the accuracy and ROC, AUC values. After comparing the base classifier's performance, we have selected the best model here, which you can see is the XGBoost model, and calculated the accuracy, precision, and recall of the for each target column of the resultant of the selected model, that is XGBoost. See, so in the code, you can see that first we have split the data into the training and the test data. Then we have used multi-output classifier and base class with base classifier linear SVC. This provided us the accuracy of 67% and 53, and ROC AUC value of 0.53, which is not that good. Then we use logistic regression as the base classifier with multi-output classifier. In that, we got a little better result of 67.7% and 0.538 ROC AUC, but it's still not good enough. Then we use the knife base uh, classifier as the base classifier. This actually reduced the accuracy to 64.7%, but it increased the ROCAC value to 0.567. Then finally we used random forest, which gave us promising result, which was 99.3% and overall RAC AUC of 0.992. But still we went one step further and performed base classification we use base classifier of XG boost classifier and got the accuracy of 99.6% and overall ROC AUC of 0.995, which gave us the best results. We, as you can see, we have plotted the, we have written all the more accuracy and ROC AUC in a tabular form to uh, to compare, and the XG boost is the best, is giving us the most prominent and the best results. We have also we have also plotted this overall accuracy and ROCAC value, and again we can see the XG boost is the best model for us. So see, this is the same overall accuracy by model, overall ROC by model, and the tabular form. Now for validation, we have uh, for the selected model, we have selected the model XGBoost and then created the classification report and confusion matrix for each column. For mood swings high, uh, we we ran this code. Also, before that, we calculated the Hamming loss, 0, 1 loss, and mean square loss. All of these losses are very low, which indicates that our model is working really good. So this is the code for creating the classification report and confusion matrix, which you can see uh, is looking very good, as we do not have any true positives or on any false positive or false negative. With this we have included in our presentation as the same, and similarly we have written the same code for mood swings medium and mood swings low, and created the confusion matrix and classification report for the same. So as you can see, for mood swings medium, we have this is the classification and report and confusion matrix, and for mood swings low, this is the confusion matrix and classification report. So for our final observations, I we have summarized our project. That is that we first collected the data, cleaned the data, and then finally we built various models with for with to address multi-output classification, which using multiple base classifiers like linear SVCs, logistic regression, knife-based random forest, and XGBoost. And the XGBoost algorithm gave us the most promising results. And then finally, we did the validation of each model of XGBoost model, and found for each column and got some promising results. In conclusion, this demonstrates the transformative potential of machine learning in enhancing the precision of mental health diagnostics. By harnessing the power of the XGBoost algorithm to accurately predict mood swings, we are setting the stage for more proactive, personalized, and effective mental health interventions. Research our research underscores the critical role of data driven insights in revolutionizing mental health care, ultimately leading to better patient outcomes and a deeper understanding to mental health dynamics. Looking ahead, we plan to expand the model to include additional predictive factors and explore the integration of real time data from wearable technology. The ultimate goal is to enhance the model's applicability in clinical settings, providing a tool for mental health professionals that could revolutionize how mood swings are predicted and managed. Thank you so much for watching this presentation.